Again, my name is César Ferri. I'm professor here at UPB, and I'm going to talk to you about machine teaching for XAI. As you know, this is the outline of my talk. Nowadays we're using artificial intelligence for very different applications, and in many areas like banks, insurances, or health, we need to get some explanations about decisions made by artificial intelligence. The field Explainable artificial intelligence tries to address this issue. That is, to give or provide human users a better understanding of the behaviors of AI systems. And in this aspect, humans we are very good at learning from examples. For instance, if I tell you dollars and euros are positive examples and Deutschmarks as negative examples, can you get a concept about this from these examples? No, just a general concept. What do you think I'm referring with these examples? Dollars and euros as positive examples and Deutschmarks as negative examples. Okay. Yeah, I don't hear you very well. What existing currency? Yeah, that's the correct. Okay, just with 3 examples, we have been able to guess the correct concepts. Okay, so in that way, we see that it's very useful to use examples to teach concepts. But in that way, we need to align the bias between models, AI models, and humans. And this is part of this work. Yeah.
But in this case, it's like a Deutsche in Euro, and but it's not really only those 3 examples, because like I think about it, and I think about like a Chinese yuan, JPY, and a Singapore dollar, Indian rupee. It's like it's not explicit, but you are, referring to the many other currencies.
Yeah.
So like yeah. So like we need to be careful. This is very explicit, but like people refer to like implicit examples as well.
Yeah. I agree.
So the other thing is like you can have like a volume over the trading. So Deutschmark trading, but like a euro is way bigger trading volume. So like you can actually have a positive, negative, having translation of the trading volume. Yeah. So the other transactions.
Yeah. Okay, so a challenge facing XAI is creating explanations that balance interpretability and accuracy, because we can get a lot of examples, but then in order to get an accurate explanation, but then we are going to lose the explainability of this concept. So this is a challenge to find a trade-off between the choice, number of size of examples, and the probability that the users identifies what the AI systems is doing. Okay. So in this aspect, we have been working in a framework, an approach that is called machine teaching. The goal of machine teaching, it can be interpreted like the inverse approach to machine learning. The idea is to look for optimal examples that a teacher should use to make a learner capture a concept. Okay, here in this plot, you can see a representative examples in which the teacher sent some examples in order to teach a concept. Which one do you think is this concept? Can you guess it? The concept? Reverse, the reverse concept. It's not right. Sorry. sorry. Okay, so this is teaching. So given a concept, the idea is to find a witness set that allows the learner to uniquely identify the concept. Okay. So the idea of this work, this approach, is to develop a conceptual, a practical setting of examples-based explanations by expanding techniques of matching teaching and applying them to explainable data. Okay, so first I'm going to give you some notions about matching teaching. Matching teaching is a domain mainly explored from a theoretical point of view and related to theoretical computer science. So the idea of matching teaching, as I told you, is given a concept to find a set of examples called witness set that allows the learner to identify uniquely this concept. Usually in matching teaching, we talk about teaching dimension as the minimum cardinality of witness sets for one concept. Okay, but there are some problems about these definitions. Like, for instance, this maximum usually could be unbound. And even if we adopt a preference-based order on concepts, the maximum is still unbound and incompatible. Okay, so these teaching dimensions, as I told you, there are several problems. And inspired by those problems, we try to define a new teaching metric that we think that is better to apply for practical problems. The idea is to, instead of, well, going to skip this, is more or less the theoretical framework about matching teaching. The idea is, instead of working with cardinality, work with size. We use encoding schema in order to encode the witness set and try to find the smaller witness set in which we are able to teach a concept. This minimal set is known as a witness set for a concept C, and this teaching size depends both on the concept and the learner. Okay, so we are going to, the thing we did is to apply this approach for a Turing complete schema or programming language. In order to do this, we need to set an order of program that is defined here, and we need to also define the F compatibility. Okay. So the idea of this approach is to use, as I told you, a Turing complete programming language, and then to develop an algorithm for the teacher and for the learner in order to find, given a concept, to find the smaller witness set in which we can teach that concept. This is the formal definition of the teacher. Also, here you have the formal definition of the learner, and we have some results about the computability of the approach. And thanks to a brute force algorithm, we were able to build what we call teaching book. In this teaching book, we have a set of concepts, and we are able to find the minimum witness set from which we can teach this concept. Okay, so in order to implement this theoretical schema, we use a very simple Turing complete language that is called P3. P3 is also known as BrainFuck. It's a very simple programming language because it has only 7 instructions that are these ones that you can see in the slides. And we consider 3 symbols in this for the alphabet, 0, 1, and dot. The operation of this P3 language are operations to move the pointer in the memory, then 2 instructions to override the symbol in the pointer cell, plus and minus, and instruction O2 outputs the concept of the tape. And in order to get loops, we use brackets. Okay? Here you can see a very simple examples of these programs in P3s. For instance, the first row, you can see the identity program is just a loop that traverses the memory and output all the symbols in the memory. Okay, you have seen these other examples. Okay, so thanks to our approach and this P3 program, we were able to create our teaching books. In these teaching books, the thing we had is programs and the smaller, according to this teaching site, the smaller we need set from which we are able to teach these concepts. Okay, we had some theoretical results about that, but the important thing in this talk is that we can use matching teaching in order to get real, in this case, using a Turing complete programming language, we are able to see that our approach can work. Okay, so how can we use matching teaching in a XAI framework? In matching teaching, usually we have one teacher that is viewed as a function from concepts to level or to witness sets. That is, a teacher that, given a concept, is able to provide a witness set. Okay. Meanwhile, the learner is viewed as a function from sets to labels examples to concepts, denoted as you can see in the slide. So in this framework, we define a correct teaching if we have the situation that the teacher is able to provide a witness set and the learner is able to get the concept from this witness set. And how can we apply this for XAI? So here we are going to consider that the learner are humans, okay? But we cannot run experiments with humans. Of course we can do, but we know that it's very expensive and very problematic. So the thing we do is to substitute humans by another machine learning model. We call this LM. That is a machine learning technique that, in a way, characterizes the human learner. Okay, we use this simplicity prior beta that is based on this on simplicity using this Occam razor principle. We also need to define a simplicity prior on example sets, and we also need to define a loss functions between the guesses from the original model we want to explain and the approximations we are getting with this surrogate machine learning model. Okay, and the idea in our approach is the following: we need to find a teacher that is able to provide a set from which the learner run by this surrogate machine learning model is able to learn, but we need to minimize the simplicity of the teaching set. We need to minimize the loss functions that is measuring the similarity between these original artificial intelligence models and the surrogate model. And we also need to consider this beta, that is the bias induced to learn the models. We define a set of values that are efficacy, facility, and validity. Efficacy is based on the beta functions that must have good optimizations when the teachers use the surrogate model for the minimization problem. We also use facility based on the simplicity of examples, and we use validity based on the loss functions correlating between the proximity of the original model and the surrogate model. And these are more or less the general schema in which we are able to provide this thing. Okay, so this is like the theoretical framework. We have been playing a little bit with this framework, with the framework with practical applications. The first thing we did was try to teach Boolean functions. So the first thing we did is to generate images from these Boolean functions. In this case, you have examples when you have A, ABD, ACBD, and we have positive or negative labels. So from these functions, we generate thousands of images and we train a deep learning model. It was this, in this case, convolutional networks. that was able to classify these images according to this functional, this Boolean function, sorry. So as a surrogate model, we use coordinate maps, okay? And as simplicity prior, beta, we use UCAN razor, measure as simplest Boolean expressions, okay? Well, and these are examples of Boolean functions and the teaching sets we were able to get thanks to our approximations. In order to see the validity of our approach, we ran some experiments with humans, and then is when the party started. Because, you know, in paper everything is very nice, but when you go and work with humans, you find a lot of problems. So for the experiments, the thing we did is this simulability approach in which we give some training examples for the humans, and then we ask with these test cases in order to check whether the humans have been able to learn the concept. Here you can see an example of the framework we use for the experiments. On the left, we have we have a robot with two boxes. We put positive examples on the left and negative examples on the right, on the green box or the red box. What do you think the robot is going to put these 5 images? Okay, so and humans needed to select that according to the guess. But here we found a lot of problems because at the beginning, you know, we were using computer science students and they have like a background of Boolean functions and everything. But instead, instead of using the letters in order to guess the Boolean functions, many of them started to see things like, oh, there is a letter on the corner on the right, so that letter is not horizontal, there are vertical. So they started to make guesses about other things not related to the original Boolean functions. So first we needed to check. Well, so we studied three frameworks. The first framework was we just put the images and nothing else. The second framework was we simplified the images. We put the letters not rotated and we increased the accuracy. And finally, we gave more information, say, to the students saying, please concentrate on letters, ignore things like placement, rotation. And it was like the best approach. Then after that, we selected this third informed approach, and we do more experiments. We compare our witness sets with respect random teaching sets. We got 22 students for these smart teaching sets, that is the sets provided by our frameworks, and 34 by random teaching sets. And we were able, in this on this left plot, you can see the results. Usually, these smart teaching sets are getting better results, not with a big difference. Even there is a case in the fourth problem where this random selection was even better than these smart teaching sets. And the problem is we found is that Boolean functions are really difficult for humans. And even there are papers saying that coordinate maps are not very well aligned with humans. So it was like a first experience. It was a bit useful, was very useful to see how to deal with humans. Recently, we are applying the same thing with time series. Time series are also a domain that is really difficult to explain for humans because there is a lot of information in time series. So the thing we are doing is to get prototypes used from this. Well, first, we are addressing the problem of time series classification. That is, we provide time series, and there's a classifier that is saying this is positive or this is negative. For instance, this is a case of the affluence of people to a mall in a city. and the time series see this flow of people depending on the hours. You can see there are 24 hours. So even with prototypes, humans are not able to find patterns from time series. So the thing we are doing is try to simplify time series using approaches like the algorithm I explained. And preliminary results, we are still working on that. We see that humans are better if we are able to simplify the time series. In this plot, you can see the positive examples are on the top, or on the bottom, you see the negative examples. Can you guess a rule for this? This is more difficult. This is more difficult. So, given that we found this quite difficult, the thing we are proposing is to perturb a little bit the time series, and then to plot the effect of this perturbation on the classification. And we see that for this example, the perturbation is not affecting for the most of the time series, but there is an exception that is on the first hours. And this is really useful because we see that usually the negative examples get lower values than positive examples for the first part of the time series. And you can see more or less the same effect here. So we need to concentrate on that part if we want to explain. And this is more or less the thing we are working. This is a joint work with University of Bergen, funded by a Norwegian research consortium in collaboration with companies, with 2 or 3 companies from Norway. And these are more or less the papers we have been working since the beginning of this project. Mainly, these first papers are related to these machine teaching frameworks and different work we have developed on machine teaching. And the last papers are related to the applications of machine teaching for XAI. We are going to present two papers in this XML, and yesterday we had a presentation in this conference of Explainable Artificial Intelligence. And that's all. Thanks.
Have any questions? The question about scalability in the construction of your teaching, because that may be many frequencies in the same way. And then
yeah, this is a really good question. Yeah, the experiment we made lasts like 2 weeks. Because of course the size of the teaching book we explored was not very big, but as the size of the characters of the strings, they grow exponentially. We cannot explain the maximum level of input output. It was like 14 characters per a string. So, but it's a good question. Yeah. That is really amazing. But we wanted to show that we can do it. At least we can do it for Turing complete programming languages.